All right, question 43 on the math subject GRE practice test. A relatively basic question, I think, for this late in the test. I don't know, maybe it's the kind of thing where if you've done it before, it's easy, and if you haven't, it can be kind of hard. What's going on in this problem is we're defining this relation on the reals. So you can kind of think mapping the reals to the reals. So here's my domain, all real numbers. Here's my codomain, all real numbers. And all the relation is this infinite collection of arrows from element over here to element over here. So one arrow, for example, would go from the element 1 to the element -2. Why would this arrow exist? Because if I plug in 1 and -2 for x and y respectively into this equation, I get a true statement. Note there would not be an arrow from 1 to -3 maybe, because if I plug in 1 and -3 for x and y, I do not get a true statement here. Anyways, what we're being asked, not in these words, is whether this relation is reflexive, symmetric, and or transitive. I think it's a good idea to understand these three terms to the point where you wouldn't need to be provided with their definitions like you are in this problem. But conveniently in this problem, they do give you those definitions. It's worth pointing out that if you have a relation that is reflexive, symmetric, and transitive, so if 1, 2, and 3 are all true, that's what's called an equivalence relation, which is another vocabulary word that I could see them testing on a similar problem. Since we're provided with the definitions, you can kind of check these things without really understanding what reflexive, symmetric, or transitive means. But it's not a bad idea to kind of understand what they mean before you go checking the definitions. So informally, the idea with reflexive is you just have an arrow from every element to itself. So pick your favorite real number, I don't know, 7. There must be an arrow from 7 to 7. Note that all you need is one counterexample to break reflexivity. I don't know if that's a word. So maybe there's an arrow from every single real number to itself except for 0. There's no arrow from 0 to 0. Then that relation would not be reflexive. If there's never an arrow from an element to itself, the relation's called anti-reflexive. But that's not asked on this specific problem. So is this relation reflexive? Well, sure, it's easy enough to check. All we gotta do is let x represent an arbitrary real number and see if x is related to x. All I'd have to do is copy this definition of xry, changing all of the y's into x's. I would say x minus x times x plus 2 equals 0. Clearly, this is always true because for any real number, that real number minus itself would be equal to 0, and the multiplicative property of 0 tells us that 0 times anything is equal to 0. So we are reflexive. What about symmetric? I think of symmetric as a step up in difficulty from reflexive because it's kind of an if-then statement. The idea with symmetric is if you have an arrow like we do from 1 to -2, then there must be some other arrow from -2 to 1. Informally, you might say that every arrow also exists in reverse. Note that this statement becomes trivially true if you have an arrow from an element to itself, right? If there's an arrow from 1 to 1, then there has to be another arrow from 1 to 1, but that arrow exists trivially. So symmetric is really only interesting for distinct elements x and y, like we see up here in this picture. There's an arrow from 1 to -2. Must there be an arrow from -2 to +1? Much like with reflexive, there's also an idea of anti-symmetric. As you could probably guess, for anti-symmetric, the idea is anytime you have an arrow, there can't possibly be an arrow from that second element back to the first element. If that's the case, your relation is anti-symmetric. Note that if you're anti-symmetric, you're necessarily anti-reflexive, because if there's a single arrow from an element to itself, then you satisfy symmetry with that arrow kind of trivially. But again, we're not talking about anti-symmetric in this problem, we're talking about symmetric. As I mentioned, symmetric, it's an if-then statement. So to check that, we first assume that we have an arrow from some element x to some other element y, and then we ask ourselves the question, is there an arrow from y back to that first element x? Maybe the slickest way to prove this, if this were a proofs test, is since we're assuming x, r, y, we can copy exactly what we see here. We know that x minus y times xy plus 2 must be equal to 0. If we multiply both sides of this equation by -1, we get this equivalent statement. Distribute this -1, we get here, and then take advantage of what the commutativity of addition, -x plus y is the same as y plus -x, and the commutativity of multiplication, x times y, is the same as y times x, and then stare at this and realize that this is exactly y r x. So we started out by assuming that x r y was true, and we end up proving that y r x is true. Looks like this thing is symmetric. If you're not used to proving things, maybe you don't like that line of reasoning, you can definitely figure this out a lot more intuitively. Right? Just recognize if there's an arrow from x to y, then x minus y times xy plus 2 is equal to 0. But the only way the product of two things can be equal to 0 is if the first one itself is equal to 0, x minus y, or the second thing itself is equal to 0, xy plus 2. First, let's work in this case. If x minus y equals 0, well then clearly y minus x equals 0. Right, because the only way you can subtract numbers and get 0 as the answer is if these two are the same number. So under case 1, we would have y related to x. What about under case 2? Well, if x times y plus 2 equals 0, then x times y is equal to negative 2. So y times x is equal to negative 2. So y times x plus 2 is equal to 0. We'd have an arrow from y back to x. So since there's an arrow from x to y, either this is 0 or this is 0. If it were this that were equal to 0, then we definitely have an arrow from y back to x. If it were this that was equal to 0, then we definitely have an arrow from y back to x. So if there's an arrow from x to y, there's definitely an arrow from y to x. We clearly have symmetry. The third thing to check is transitivity. I think of it as the most challenging of the three. It's often the one that tricks people up. Even if you understand what transitivity means, it's easy to kind of forget a special case. Like the relation does not equals, for example. Turns out that's not transitive, although you might think it is. Mess with that for a little while and convince yourself of that fact. Just like there's an idea of anti-reflexive and anti-symmetric, there's an idea of anti-transitive, and it's exactly what you would think. If there's an arrow from x to y and an arrow from y to z, then there can't possibly be an arrow from x to z in order for the relation to be anti-transitive. But that's not what we're talking about here. Here we're talking about transitive. The idea with transitive is, much like symmetry, it's an if-then thing. We start by assuming that we have two different arrows. I kind of like to draw it like this. We got an arrow from some element to some other element, maybe from x to y, and then there's a second arrow from y to some other element, z. And the question is, if these two arrows already exist, must there be an arrow from x all the way out to z? Kind of a shortcut to get from x to z. Well, I bet you could show transitivity kind of with a similar proof to what we did here. Start by assuming x are y and y are z, and then algebraically manipulate things until you come up with x are z. But I think it's easier to kind of mimic this intuitive approach. All right, we know that there's an arrow from x to y, and we know there's an arrow from y to z. The question is there an arrow from x to z? Well, let's first consider x r y. That tells us that x minus y times xy plus 2 is equal to 0. So either, maybe case 1, x minus y equals 0, or case 2, xy plus 2 equals 0. Regardless of which case we're in, I'm a little low on room, so maybe I'll throw it over here. We know that there's an arrow from y to z. So that tells us that y minus z times yz plus 2 must be equal to 0. So let's suppose we're over here in case 1, x minus y equals 0. Well, since y is related to z, either y minus z is equal to 0 or yz plus 2 is equal to 0. Right? Maybe this is case 1a and this is case 1b. Similarly, if we were in case 2, because there's an arrow from y to z, either y minus z equals 0, I guess this would be case 2a, or yz plus 2 is equal to 0, what we would call case 2b. So we have these four different cases to consider. In case 1a, y minus z equals 0, and x minus y equals 0. And the question is, does that guarantee there'll be an arrow from x to z? Well, remember there's an arrow from x to z if x minus z times xz plus 2 is equal to 0. If x minus y equals 0, x is the same as y. If y minus z is 0, y is the same as z. So x is the same as y is the same as z, that means x is the same as z. If x is the same as z, this difference is 0, this product is 0, there's an arrow from x to z. It looks like in case 1a, we would have an arrow from x to z. But that's not enough to show transitivity. For transitivity, we need an arrow from x to z for each of these four cases. So now let's check case 1b. Well, remember, because we're in case 1, x and y are the same number. So if yz plus 2 equals 0, since y and x are the same number, xz plus 2 equals 0. But if xz plus 2 equals 0, this is 0, so this product is 0. So there's an arrow from x to z. Looks like in case 1b, we're good as well. What about case 2a? Well, here y and z are the same number, and xy plus 2 equals 0. But since y and z are the same, I can change this y into a z and say that xz plus 2 equals 0. If xz plus 2 equals 0, this is 0. The whole thing is 0. There's an arrow from x to z. I get symmetry again. The most challenging case is case 2b. I think it's worth rewriting. What we know is that xy plus 2 equals 0. And that yz plus 2 equals 0. And our question is, does that imply that x minus z times xz plus 2 is equal to 0? Well, let's see. If xy plus 2 equals 0, then xy is equal to negative 2. If yz plus 2 is equal to 0, then yz is equal to negative 2. But if xy equals negative 2 and yz equals negative 2, then xy equals yz, which implies that either y equals 0 or that x equals z. If you have a hard time seeing that, subtract yz from both sides, and then factor out a y from each term, and then apply the multiplicative property of 0. Either y equals 0 or x minus z equals 0. So first, what if y equals 0? Y doesn't equal 0. How do I know that y doesn't equal 0? Because x times y plus 2 equals 0. And if y equals 0, this product is 0, and 0 plus 2 cannot possibly equal 0. Since y can't possibly be equal to 0, x minus z must be equal to 0. But if x minus z equals 0, this difference is 0, so this product is 0. So we get an arrow from x to z. Case 2b is a little bit subtle. You have to rule out the case that y equals 0. But conveniently for test takers, even if you kind of forget about that, you'd come to the same conclusion, just with slightly flawed logic, and still get the answer correct. Anyways, we've shown that this relation is reflexive, symmetric, and transitive. Therefore, it's what's called an equivalence relation, and therefore the answer to the question is E.